Good morning, physics. All right, today I'm going to walk through the calculations for the ballistic pendulum lab and for ballistic pendulum problems in general. The difference between the lab and the problems is you've collected most of this data rather than actually calculating it or being given it. But the process is the same for pretty much any ballistic pendulum problem, with one exception that we'll talk about in class when you guys get to it on the homework. So we are going to be considering three distinct instants in time. All right? The instant before the collision takes place, so I'm using the old style ballistic pendulum where we actually fired a bullet into a block of wood. But the block of wood is just the pendulum, and the bullet would be your brass bullet that you were firing, except it was a ball instead of shaped like a bullet. So this is the bullet, this is the block. They have not actually collided, but they are just about to. Okay, that's A. B is after they have collided, the block, or all of the, I almost said the wrong word. The bullet has impacted the block, and the block has started to move, but it has not actually changed its position yet. So we're talking about a very specific instant in time. The bullet has hit, but the block hasn't gone anywhere yet. So it's still in its original position, the same spot where it was here. And then C is going to be after the block and bullet together have swung, they've risen to some point and come to rest right before they would then swing back. Now, for your apparatus, it actually clipped into place so that it couldn't fall back down. But with an actual block of wood, obviously you can't do that. It rises and then it falls back down. So we are going to be looking at these three instants in time in order to solve this problem, or in order to set this up. So I don't know if you can tell in the video. It doesn't look like it. I'm looking at the background behind me. It doesn't look like you can tell. But I'm using blue for A, green, no, good Lord, I can't even tell. Purple for B, and green for C. So yeah, there's that. So hopefully that will be a little easier to see as I go on. Maybe if I turn on the lights. I'm going to turn on the lights and see if that helps. That helped a little bit, and the glare isn't so bad that you can't read it. So let's get going. Okay. A and B represent the before and after of a collision. That means that we can use the law of conservation of momentum to compare these 2 points in time. So we're going to calculate the momentum in A and the momentum in B. And by calculate, I mean I'm going to write out the equations for them, but not actually solve them because we don't have all the information yet. So let's start with A. So momentum in A is equal to the moment. Oh, there is one other thing I almost forgot. I almost forgot this yesterday too. We're going to call the bullet 1 and the block 2. Okay, and that's going to be for the whole thing, not just for A. So anytime you see a subscript 1, we're referring to the bullet. Anytime you see a subscript 2, we're referring to the block of wood or the pendulum bob. So the momentum at point A is going to be equal to the momentum of the bullet plus the momentum of the block. Now we can calculate that, or we can sub in the actual momentum equation, which is P equals mv. So PA is going to be equal to the mass of the bullet times the velocity of the bullet at point A. That's important. Okay, it's the velocity at this instant in time, not the velocity of the bullet way down there. Okay, so at point A, plus the mass of the block times the initial velocity, or the velocity of the block at point A. So that will give us the momentum at this point in time. Then, after the collision takes place, this is an inelastic collision because both objects are now stuck together. They're moving together. So the momentum at point B, PB, I keep putting the B at the bottom. This is a lowercase p. The momentum at B is going to be the momentum of mass 1 plus mass 2, because the two of them are stuck together. And that's not real easy to see. So I'm going to erase that and rewrite it a little bigger, because I'm getting small. So PB is equal to P1 plus 2. So both objects are now stuck together. What that translates to is that the momentum at point B is equal to the sum of the masses times the velocity that they share at this point in time, B. Now, the important part here is that because of the law of conservation of momentum, this is the initial, this is the final after the collision. So this is the before, I'm pointing at the wrong one. This is the before, this is the after for the collision. Law of conservation of momentum says these must be the same. So we can set them equal to each other, which is what I'm going to do now. So instead of PA, I'm just going to start here. So M1 V, wrong V, V1A plus M2 V2A is equal to M1 plus M2 times VB. Now, if we look specifically at your lab, we know the mass of both the bullet and the block. So we know M1 and M2 on both sides of the equation. We do not know the initial velocity of the bullet. We do not know what velocity this bullet had when it came out the barrel of the gun. So we don't know that. That is an unknown, which is fine. We can solve an equation with one unknown in it. That's pretty easy. We do know the initial velocity of the block, or pendulum bob, because it is just hanging there. It's not going anywhere. That means it is stationary, and its initial velocity is 0. Anything times 0 is also 0. So, since the mass is being multiplied by 0, this goes away and is now equal to 0. We know that, we know that. We do not know this. This is the velocity that the bullet and the block have the exact instant after the collision has taken place, before it's moved any, because as soon as it starts to move, it's going to start to slow down. But at that fraction of an instant, we know that this velocity times the sum of the masses is equal to the momentum of the bullet, because the block isn't moving. But this is one equation with two unknowns, and we can't do anything with one equation and two unknowns. So, we have to find another way to finish this problem. The way we do that is by looking at energy, because while energy is not conserved, mechanically speaking, in a collision, it is conserved after the collision. So from the time after the bullet has impacted, from that point in time until the block rises and stops, energy is being conserved. So the energy that the block and bullet together have here has to be equal to the energy that the block and the bullet have here. This is useful, and I will show you why if you haven't figured it out yet. Okay, we don't need blue. So, now we're looking at energy. So at this point, this is the lowest point in the problem. The block is hanging as low as it can go. Once the bullet hits it, the strings that it's attached to, or the pendulum rod in the case of our experiment, causes it to rise as it tries to move because it can't get any closer to the spot where it's attached, and it can't move in a straight line. The strings pull on it, and so it has to swing up. So this is the lowest point in the problem. That means that we can say h equals 0 at this point B. If h equals 0 here, then the only energy that this block and bullet have is kinetic energy, translational kinetic energy, which is convenient because that means that we can use the KE equation. So kinetic energy is equal to mv squared over 2. So the mass of the system is the mass of the bullet plus the mass of the block. So m1 plus m2. Just like it was here for momentum. Times the velocity of that system. The velocity at this point is the same as it was when we were talking about it in momentum. So we have already called this velocity VB, and this is the velocity that we didn't have that we need in order to calculate this velocity, which is the one we actually care about. So it's a good thing that this is in the equation. That's a good sign. So VB squared divided by 2. That is the energy at this point in time. Drop my lid. Then we look at the final position at point C. Now the energy here, remember, this is that instant when it has risen to its max height and it stops moving. When it stops moving for that fraction of an instant, its total kinetic energy is 0 because it is not moving. If its kinetic energy is 0, that means that all of its energy is potential energy, specifically gravitational potential energy in this case. So we can use our PEG equation. I'll write that in a weird way, apparently. So gravitational potential energy at point C is equal to the mass mgh. So the mass of the system times the acceleration of gravity, which is the constant g, times the change in height, which is handily known here. So the mass is still m1 plus m2. G is g. And then delta H is how much the system has risen between points B and C. Now, this is the height that you directly measured in the lab. Okay, you actually measured how much farther up it was. Now, you had to do a little bit of a calculation to get it, but that's the height that you're using. You have 5 of these. You're going to you're going to average those and get one average delta H. Plug that 1H in here, and you'll do the calculations that I'm about to show you. But I'm getting ahead of myself, so I'm going to back up. Because of the law of conservation of energy, the energy here has to be equal to the energy here, which means we can set these two equations equal to each other, just like we set these two equations equal to each other. So, get my markers ready. The kinetic energy at B has to be equal to the gravitational potential energy at C. So, purple, m1 plus m2 times the velocity at point B squared divided by 2 has to be equal to the sum of the masses times the acceleration of gravity times delta H. Like I said, we know delta H, we know G, And we know both masses. The only thing in this equation that we do not know is V1B. Sorry, VB. So we take this equation, we solve it for VB, then we take VB and plug it in here and solve this equation for V1A, the initial velocity of the bullet. And that will allow us to calculate the initial velocity of our bullet. Now, that is how you do part 1 of the calculations for the ballistic pendulum lab. Part 2 is kinematics, and I have already said in class, if you get stuck on that, we can take some time in class and I can review those. Remember, this lab is due on Friday at midnight, so don't wait till Friday at 11 p.m. to let me know that you're having trouble getting that calculation done. You only have to do this calculation one time because you're only going to have one H to plug in because you're using your average H. So use H to get VB, and then use VB to get V1A, the velocity of the bullet. That's it for this video. Hope this helps. And I will see y'all in class.